Alright, so we are in Algebra 2. Today's date is Monday, September 23rd, 2019. Make sure that we have our name and date on our paper, 9/23. There it is. Alright, so we are dealing with the imaginary unit today, teaching you about our shadow dimension objective. Who wants to read it? Caroline.
Find what I raised to a power is and simplify negative square roots with I.
There it is. So our warm-up was simplifying square roots without I. That was back over here. And now we're going to simplify square roots that do have I in it. So, has anyone heard of the imaginary unit before now? Does anyone know about the shadow dimension? Chewy Hood?
Oh, sorry.
Not a single person? Okay, the definition of I, and we are going to be doing this a ton if you take pre-calculus next year. My pre-calc students are doing like crazy things in the complex realm. Square root, or I is equal to the square root of -1. Everyone write it down. This is a definition you have to have memorized by heart. You need to know what I is. Is there a question or you have an answer? Question, go for it.
Answer.
What's up?
I is equal to -1.
I squared is equal to negative?
Wait, what did you say?
I just said that I is equal to the square root of -1.
So I is equal to the square of I is equal to the square of -1.
Yes.
Is that the correct answer?
Answer to what?
To that.
I already gave it though.
I know. I is equal to the square of -1.
Yes. Yes.
Is that the correct answer?
Yes.
Can I turn in my participation card?
You may not.
Okay.
It's a good attempt though. All right. So, coming back here, that is kind of weird. So if I come to my calculator, even if I come here, if I do square root of 9, it gives me 3. Let's see what happens when I do square root of -1. It doesn't like that. In fact, if I go to any calculator, let's go to a new calculator up here. If I go to any calculator and I try to do square root of -1, it will tell me that doesn't exist because it is limited to the real dimension. Square root of -1. Undefined. I'll zoom in here so that we can all see it. Square root of 1 is undefined. It doesn't like that. We are going beyond calculators today. Your calculator cannot handle what's about to happen. So, square root of -1, I'm telling you it does exist. It is equal to this imaginary unit I. Let's deal with some easy things. What happens if I were to square both sides? What happens if I get I squared? Is there a quiet raised hand who wants to take a guess? What happens if I square both sides? Is there a quiet raised hand with a card out there? Oh, Colby, yes.
Plus or minus 1.
It would be a good guess. So it would be true if the definition was plus or minus square root of -1. But if I just square it, it's even simpler than that, and it is... Careful. Try again. Okay, so this is what I'm doing. I have I is equal to the square root of -1. I'm going to square both sides. So this side on the left is squared, this side on the right is squared. What happens on the right-hand side, Colby?
-1.
There it is, -1. Everyone write it down. I squared is -1. If I were to square both sides of this, I get -1. Which is weird to think about. Because before I've told you, anything squared is always positive. For example, -3 squared is always positive 9. Now I'm telling you something different. Now I'm saying if you square something with a complex number in it like I, then you can get a negative. If you sound like you're confused, Jane, you can do that later.
Sorry, did you
If you're confused, if you're scared, if you think that I've lied to you your whole life, you're kind of right. Let's try a harder one. I to the power of 3. I'm going to write this as I to the power, thank you, I to the power of 2 times I to the power of 1. Everyone write that out as well. I am allowed to do that. That is a rule of exponents. I'm really just adding the exponents. Using this little trick, does anyone want to tell me what I to the power of 3 is? Can someone change I squared and I to the power of 1? Do you have your card, Ellery? Yeah, Ellery.
It's still just -1.
Careful. Well, what's I squared?
Oh, that would be 1. So it's
I squared is
I squared is
-1, and then I to the power of 1 is just
-1.
just I.
Oh, it's just I.
So what's -1 times I?
-1I.
Negative I.
I.
There it is. Thank you. I'll take your card.
Wow. I did not see that coming.
No, I didn't mean to be negative. That was negative, sir.
Sorry.
How is that being negative to myself?
Did you just die?
Nope. Oh, that was negative. You just assumed the worst is gonna happen.
Brian will protect you. Someone needs to heal Brian, though. Let's try I to the power of 4. Using the same trick where I break it up into powers. Maybe I think of I to the power of 4 as I to the power of 3 times I. Or maybe I to the power of 2 times I to the power of 2. I want you guys right now, write out what I to the power of 4 is in terms of other different powers. I'll give you guys about 10 seconds to do that. After you write out those powers, then tell me what is I to the power of 4. Now look at your neighbors. Look at the left. Look at the right. Are they putting the same thing as you? Are they getting the same answer as you? Get help from people that are around you. Chewy, feed off the desk. Are people getting the same answers? Jaden, laptop shut. All right. Quiet raised hand. What did you do, Beverly?
What did I do?
Yeah, what do I write here? How'd you get an answer?
I squared
I squared
times I squared
times I squared equals 1 because you did negative 1. I squared is the same thing as negative 1. I squared is also negative 1. Negative 1 times negative 1 is positive 1. Thank you, Bev. It's kind of a weird concept to think about. It's hard thinking in this shadow dimension. What happens when we do powers? So what I want to do now is look for a pattern. We did a warm-up where this was very similar. So if I did I to the power of 0, anything to the power of 0, even in the shadow dimension, this works. Anything to the power of 0 is, shout it out, 1. I to the power of 1, we wrote that out also, is just I. Anything to the power of 1 is just itself. I to the power of 1 is just I. Bless you. I to the power of 2. When the power is 2, the number is what? Negative 1. Keep writing them out. I to the power of 3. We got that one was right here. That was negative I. I to the power of 4 was, bless you, 1. Someone try doing I to the power of 5. Maybe you have scratch work to do up in the top right. You have a bunch of white area. Try I to the power of 5. Maybe someone can even predict what I to the power of 5 is going to be before they do the math. All right. Quiet raised hand. What is I to the power of 5? India.
It's gonna be I.
It is indeed I. Thank you, India. I'll come get it. I to the power of 6. Look at the pattern. You don't even need to do math now. I to the power of 6. Anyone? Quiet raised hand. I to the power of 6. Sam. Ooh, careful. So the pattern goes 1 I, negative 1, negative I. 1 I. Sam? It is indeed negative 1. Thank you, Sam. And Colby, each of these are 50 XP, right? You got them? What about I to the power of 7? Who has that one? Cheyenne. It is indeed negative I. What about I to the power of 8? Quiet raised hand. Atziri. It is indeed 1. Thank you, Atziri.
You said that series like, oh wait,
1.
Siri on this.
Oh, weird.
7
All right, so, question?
I don't get this at all.
That's right.
At all?
He took each.
All right.
Like, how does
Yeah, 'cause you're
I squared plus 1 I to the first power equal negative I. How does that even work?
All right, yeah. Let me run back through this, the logic. So far we have I is equal to the square root of negative 1. We're all nodding our heads. That's the definition. Assuming that Mr. Sindel is right, then we're okay with whatever follows. I squared is negative 1 because I'm going to square both sides. If I square the left, I get I squared. If I square the right, the square root and square cancel each other out. Everyone is okay with this. Okay, I to the power of 3 is I squared times I to the power of 1. It's the same thing as saying 2 to the power of 3 is equal to 2 to the power of 2 times 2 to the power of 1. Well, 2 to the power of 3 is 8. 2 to the power of 2 is 4. 2 to the power of 1 is 2. 2 times 4 does equal 8. I'm allowed to use rules of exponents to say 2 and 1 are added when I'm multiplying the bases. So far, so good. From there, I'm just using the same rules where I'm multiplying -1 times I equals -I. -1 times -1 gets me to 1. So maybe I can, you want to ask the question in maybe a different way and I can help better?
I don't know.
So if I were to do, for example, I to the power of 5. I to the power of 5 is equal to I to the power of 3 times I to the power of 2. So Lorena, what's I to the power of 3? You already have the definition down here. I to the power of 3 is -5. What about I to the power of 2? -1. What's -1 times -I? Negative times a negative is a positive, and what do I have left? Positive 1i. So I can say 1i, or I can just say I. So I to the power of 5 is I. I to the power of 5 is I.
Yeah.
Ask the question, Sam. Honestly?
Is the shadow does this is the shadow realm a real thing, or did just a bored mathematician make some rule?
Probably made it up.
So
I'm trying to figure out
He must have been on drugs if he entered the shadow.
He was on a purge.
Sorry, I don't know. I don't know the history.
So imaginary numbers, they are useful. They're applicable to real life, not normally things that you do in everyday life. If you're an electrician, you'll be using imaginary numbers. They're really helpful with cyclic things like how electricity works.
Okay.
So they are real, if that's anyone's question. They just are called imaginary. Yes, a bored mathematician did come up with it, just like a lot of things. If you study math at the high level, you'll be doing things with weird, like Submanian manifolds and like things I can't even comprehend. None of them are useful yet. The whole idea of math isn't to be useful, usually it's to be fun. So Einstein's theory of relativity, it was just a theory. It was, well, so far as we know, it's real, but it was just a fun math topic. People had no application of Einstein's theory of relativity. Does anyone know by quiet raise hand why we care, why it's useful? It is useful because satellites are moving so fast that it actually affects how fast their time works, or the speed of time. The speed of time slows down or speeds up depending on how fast you go. Because of Einstein's theory of relativity, which had no application before satellites, is now used so that you can get within 10 feet of each other using GPS. If we did not have Einstein's theory of relativity, satellites would be so imprecise that I would be off by like a mile. Now, because we have this random math idea that we can apply to the real world, we can be more accurate. And that's usually how mathematics works. We have these random areas that we can suddenly apply to the real world that we didn't know that we could do that. So that's kind of the reason that I'm teaching.
Can we learn about the satellites?
We could. It's kind of a hard lesson. It's way harder than this.
I'm kind of lost, but I'll just have Colby teach.
I is equal to the square root of -1. Know that the definitions, I squared, I to the power of 3, I to the power of 4. You need to have these 4 definitions down. They all stem from the fact that I is equal to the square root of -1. From there, I'm just going to find a pattern. I know that the pattern repeats every 4. 1i, -1i. 1i, -1i. 1i, -1i. It repeats every 4 digits. Every 4 powers. Does everyone see that this repeats? You can give me a simple head nod, no or yes.
Yeah.
If the cycle is 4, let's go ahead and divide the power by 4. 0 divided by 4 is 0. It has no remainder. 1 divided by 4 has a remainder of 1. 2 divided by 4 has a remainder of 2. 3 divided by 4 has a remainder of 3. 4 divided by 4, though, is 1. 1 remainder. So if I go 4 divided by 4, 4 goes into 4 one time, 4 minus 4. The remainder here is 0.
Does that repeat it?
This should also repeat.
So it's 1, 2, 3.
Then it goes 1, 2, 3, 0 again. Yes. Because 8, I'll take it. 50 XP to Jane.
Wait, I think I'm messing up.
8 divided by 4. This 8 divided by 4 is 2 with a remainder of 0. I'm helping you unlock the pattern so that you can figure out these questions. The whole point, half of today's lesson is this. How do you figure out what I to the power of 81 is? How do you figure out what I to the power of 123 is? Obviously, I don't want to have to count out all of these cycles over and over again. I'm trying to give you the pattern so you can jump straight to the answer. And I'll show you how to do that. I to the power of 81. Well, what we're really doing is we're taking the power divided by 4 to get the remainder. What's 81 divided by 4? What is the remainder? I'll do it with you guys. Write it off to the side. If I go 4 into 81, write it out with me. 4 goes into 81. Well, 4 goes into 8 twice. 4 times 2 is 8. 8 minus 8 is 0. And I'm going to bring down the 1. I'll pause. I'm just doing 81 divided by 4. Next, 4 goes into 1 how many times? None. 4 cannot go into 1. 0 times 4 is 0, and here's my remainder. My remainder is 1 minus 0, which is 1. My remainder is 1. Notice the pattern here. 1 always links up with I. 1 always links up with I. 1 over here would also link up with I, which means I to the power of 81 is I. Jaden,
What?
that's so inappropriate.
How?
My goodness.
It's the
Jane.
numbers that were on the board.
So,
Okay, I will take 5. That's fine.
I don't know how to spell inappropriate. Brian will take some damage for you.
I didn't know that was bad. It says right
Question, Beverly.
Why are you dividing by 4?
I'm dividing by 4 because I know that the cycle repeats every 4. It goes 1, 2, 3, 4, or it goes 1, 2, 3, 4, then repeats. 1, 2, 3, 4, then repeats. If the cycle is 5, I would be dividing by 5. This is how we find patterns with cycles. However long the cycle is, we divide by the length of the cycle. It's a quick way of figuring out where in the cycle you are when you're really, really far away, like you're at hundreds or thousands of numbers away. Let me boil this down for you guys. How much room do we have on the back? I think we can, so right about here, let's go ahead and I will give you the procedure. Step number 1, do the power divided by 4 to find the remainder. Then you have the following table. If the remainder is 0, 1, 2, or 3, then the number, and you can just match this up with the table above. If the remainder was 0, in our table we said remainder of 0 goes to 1. If the remainder is 1, it goes to I. Question, Beverly.
Are all the problems you're going to do, is it going to end up with a remainder of 0, 1, 2, 3?
Yes, because we're dividing by 4. So if I divide by 4, it's impossible to get a remainder of 5 because then I could have divided by that more.
And what if you get a negative? Is it
I'm not going to give you a negative.
Power divided by
Negative, is that right? 1I, negative 1, negative I? That's right. Question, Ellery?
Doesn't it also work that like an even number is always 1 and an odd number is always I? And then you can look at the remainders for the positive and negative.
Yeah, that's another way to do it. Yeah, India?
Oh, I feel like you have to use the other part of example 1 for me to ask my question.
Do
Because
what for
I
number
was
1?
Ask if like the last digit is the remainder, because it works for the two in example 1.
It's really close. I can give you an example where that doesn't work though. So 81, the remainder was 1. So write it down. Remainder is 1. Because the remainder is 1, 1 matches with the number I. I is the answer. Let's apply our procedure again. Our procedure again is take the power, divide by 4, and find the remainder. So the power is 123. I'm going to say 4 goes into 123 how many times? Well, 4 goes into 1 0 times. 4 goes into 12 3 times. 3 times 4 is 12. Do some subtraction. And you find that the remainder is 3. I'll let you guys catch up.
Oh, come on. What did I do? Okay, you can take that page. Can you tell me what I did?
You're speaking out of turn?
I didn't even say that.
The remainder is 3. Are there questions about how the remainder is 3? If the remainder is 3, we know by the table above and below, if the remainder is 3, the answer is negative I. Anna.
How do you know if it's going to be a positive or negative I?
So I know that if it's a remainder of 3, 3 just automatically matches up with negative I. 3 always matches up with negative I.
Then farther in, just multiples of 3 are always negative I?
That's not quite true. For example, 9. 9 is a multiple of 3, right? I to the power of 9. But if I do 9 divided by 4, I get a remainder of 1. This has a remainder of 1. And 1 always matches up with I, so this one is going to be equal to I.
Okay.
All right, well, I'm going to leave you with this. We can work on it with Khan Academy and see what happens. Hopefully I can answer questions then. Let's talk about simplifying square roots. So one of these you did for the warm-up. The other one is brand new. See if you remember how to do simplification of square root of 20, simplification of square root of 45. Do that now. Make a factor tree where you're looking for perfect squares. I'm going to be walking around and helping you guys out. All right, quiet raised hand. Who can do a factor tree for square root of 20? Everything in your factor tree should have square roots in it. Beverly, go for it.
Be the square root of 4 and the square root of 5.
Cool.
And it's going to be 2 square root of 5.
There it is. Thank you. All right, just going through this again. Whenever you do a factor tree, make sure that your factor tree, if you start with square roots, everything in your factor tree also has square roots. You're looking for something that is a perfect square. That way I can square root it, like 4. 4 can be square rooted into 2. That's how you simplify square roots. You're looking for a factor tree where you get a perfect square. Jaden, are you okay?
Yeah, I was just looking for something.
So same thing, square root of 45. I'm making a factor tree that has square roots. Who can do that one for us? If you have a quiet raised hand. Ellery.
Square root of 9 and the square root of 5. And that goes to 3 square root of 5.
Thank you. Again, looking for that perfect square. It's kind of hard to see in 45, but 9 is a factor of 45 to get this. Give me a fist of 5 on how well you can do normal factoring without complex numbers, without imaginary numbers. I see a 2, a 4, 5, 5, 4, 4, 5. All right, I know who to work with after this. All right, so
Wait, what was your question?
my question was, fist of 5, how well can you do normal factoring? All right, so from here, this is going to be the same thing, except you also have a third branch. So on square root of 20, there are going to be 3 branches instead of 2. You will always start with 3 branches instead of 2. Your third branch is going to be your new branch. These other 2 branches are exactly the same. Square root of 4, let me write that better. Square root of 4, square root of 5. The third branch is always, always, always going to be negative 1.
Why?
That's a great question. Why should this be negative 1? Well, negative 1 times 4 times 5 is negative 20. The reason I always choose square root of negative 1 is that is the definition of an imaginary unit. Quiet raise hand. What is the square root of negative 1? Look at the very top of your notes. What is the square root of negative 1? With a quiet raised hand. Caroline. I. This now changes on my final line down here to 2I square root of 5. You can put the I before, you can put it behind. It doesn't really matter. Usually mathematicians put them in front. So by the same logic, square root of 45 should have 3 branches as well. Square root of 9, square root of 5, and the square root of negative 1. Question, Leo.
Why isn't it a capital I?
That's a good question. I don't know. They just randomly decided with lowercase I.
Can I write a capital I? Can I as well?
I would appreciate it if it was lowercase I because it's mathematically standard. You can just start from here on out doing lowercase I. If you do capital I in Khan Academy, it will not be considered correct. And then this one is going to be the same thing where I have 3I square root of 5. If I were to summarize this in one step, I would say do like you normally do, but just add an I. If you ever have a square root of a negative, do a normal factor tree, but make sure you have an I in there somewhere, not inside the square root, on the outside of the square root. That is my one-step summary. Let's try it again. You guys, on the back, show me these 2 examples, square root of negative 72, square root of negative 33. You tell me what those are. I'm going to be walking around and helping people. All right, quiet raise hand. Who can do a factor tree of square root of 72 with that 3rd branch and make sure that at least one of the branches has a perfect square in it? India.
It's going to be the square root of 9, the square root of 8, and the square root of negative 1.
There's our first 3 branches. Perfect. Continue on.
Then you're going to go the square root of 2 and the square root of 4. And then off to the side, you get the square root of, off to the side of this, where I had the square root of 9 times the square root of 4 times the square root of 2. And the square root of 9 is 3. The square root of 4 is 2. And you can't do any square root for the 2, so it'd be 6I to the square root of 2.
There it is.
Yeah, I'm so lost.
All right, we'll go through that again.
Have homework.
We'll go through that again. We're always going to have homework. So, we start with our factor tree. Sam, what is one of the 3 branches always going to be when I have a negative square root? Sam. One of the 3 branches will always be
Negative 1.
negative 1. So that's where the negative 1 came from. In order to get this negative, turn it into a negative 1 for one of the 3 branches. These 2 over here, make sure that one of the 2 factors for the remaining 2 branches is a perfect square. A lot of people were trying to do branches that did not have a perfect square. We have 9 as a perfect square because the square root of 9 is 3. The square root of 9 turns into 3. So 9 is a good square root to do. You could have done this factor tree a bunch of other ways too. You could have done 36 and 2. 36 is a perfect square. That would have been okay. Square root of 8 still has a perfect square in it, which is why we keep going. We keep going because there's a 4 in there. 4 times 2 is 8. 4 is a perfect square. Keep going until you're out of perfect squares. Square root of 2 times square root of 4 is square root of 8. So from here I have these 4 numbers. We just squish them all together. Square root of 9. Square root of 4. Square root of 2. Square root of negative 1, which was I. We just squish them all together and then we simplify. Square root of 9 is 3. Square root of 4 is 2. Square root of 2 is still square root of 2. I is here. We just kind of switch their position. And then from there, you just keep multiplying. 3 times 2 is 6, and you just keep squishing and refining and reducing and simplifying. Ask me a question, Anna.
Does 6 and 12 work?
6 and 12 do make 72, but unfortunately 6 and 12 are neither of them are perfect squares. So you have to have a factor tree that has perfect squares. Some of these numbers, at least one of these branches needs to be a perfect square.
Interesting.
Other questions?
Wait, except doesn't if you had 12, if you break it down 4, which is 2.
So 12 does have a perfect square in it, but then your two branches are taking from each other. So you can do it that way. It's a little bit harder to teach it that way. It'll be more
Is there
confusing.
like a rule or trick for looking at the number and knowing if it will have one branch that's a perfect square and one it just or know that there is not one? Or
There
you just
is,
have to
and
check?
it's a slightly longer way. So the question was, is there a trick for knowing if you have a perfect square? And the answer is, you just do a normal factor tree of 72. So I could go 2 and 36, 18 and 2, 9 and 2, 3 and 3. If you do a perfect factor tree, then you're looking for pairs. Pair of 2s, pair of 3s. So these turn into normal numbers. This pair of 2s is this 2. This pair of 3s is this 3. This leftover 2 that doesn't have a pair, because there's no pair, it stays underneath the square root. And of course, you still have to have your square root of -1. So this is the old way that I used to teach, but I felt like this way was less confusing.
Did we do 1
Yeah.
7?
We did. Alright, and I'm going to finish off example 3 for everyone. Example 3 is one of those weird ones where, yes, you try to do 3 branches, 1, 2, and 3. One of the branches is always square root of -1. But the problem is, there is not a perfect square that goes into square root of 33. One of these branches cannot be a perfect square. You can only get square root of 3 and square root of 11, neither of which are a perfect square. You might have that happen. If this happens, the answer is just I square root of 33. You cannot touch the square root of 33. You can pull out an I, though. And there's the answer. I square root of 33. The answer back up here was 6I square root of 2.
Now can I go to the one?
And now you may go to the banyo. Yes.
Why is there why is
Banyo.
It's
Never
fun.
mind.
Other questions about this lesson? All right, you may begin on Khan Academy.